Okay, today's video is about heating and cooling curves. So a heating or a cooling curve basically looks something like this. And in this case, this is a heating curve because we're starting at a lower-ish temperature down here and we're going to a higher-ish temperature up here. Okay, there's multiple different regions here. The first spot where it gets flat, this spot right here, is what we refer to as the melting point. Okay, if you think about it, it could also be considered the freezing point when you're talking about a cooling curve. Okay, and then this flat part right here is what we call the boiling point. Now notice that when you're at the melting point or the boiling point of a heating curve or a cooling curve, notice that the temperature stays flat. So let's say we're taking some ice and we're going to get it until all of the ice has melted. Okay, that would be that and let's say we're starting at, I don't know, -5 degrees Celsius. And here the melting point or the freezing point of water is 0 degrees Celsius. Okay, in order to get it to the point where, again, here's our heat added on the bottom. In order to get to this point right here, we're going to add heat, add heat, add heat. And as we're doing that, the temperature of the ice is going to go up until we reach 0 degrees. At that point, we're going to still keep adding more heat, but notice that the temperature doesn't change. Okay, the temperature changes once now all of that ice has turned to liquid. Now the liquid is going to heat up even more, and then as that liquid gets to the boiling point, as it starts to boil, again, you're still adding more heat, and then again, while that water is boiling, the temperature doesn't change. So now we're at 100 degrees Celsius. Okay, and that's one of the advantages of using, like in a laboratory setting, one of the advantages of using like a boiling bath of water over like a flame is, depending on how close or far away you are from the flame, it'll be hotter or colder. But when you put something to heat it up in a boiling bath of water, you know that temperature is going to stay at 100 degrees. Again, until all of that water has been turned into a gas. And then again, if you keep adding heat, you can add more heat to that steam, and then of course the gas is going to get hotter. Now, when you're doing problems with heating or cooling curves, obviously you've got 3 parts right here where it's going up, and on a cooling curve, which you'll see here in just a minute, it's going to be the opposite. Something like this, and then it goes down. Okay, and same thing, you've got 3 parts where it's where you've got that slope, and then you've got 2 parts here where it's flat. Okay, so when you're doing problems with these, whenever you're dealing with this part, or this part, the way that you calculate the amount of heat it takes to get somewhere is you use Q equals mc delta T. Okay, anytime you're at this part right here or this part right here, you're using the enthalpy, and it's either the enthalpy of fusion, which again is melting, or the enthalpy of vaporization, which is, of course, this one here when you're vaporizing something. Okay, and so let's say you're going from this point here, again, all the way to this point here. Well, then you would use Q equals mc delta T for that part, and then you would add it to the enthalpy change for that part right there. Okay, let's look at an example of what that would look like. So aluminum metal can be recycled from scrap metal by melting the metal to evaporate the impurities. Calculate the amount of heat needed to purify a mole of aluminum, originally at 298, by melting it. So basically what we're doing here is, yes, we're starting right here. It's solid. So this is a solid, this is a liquid, and then right in between here, you're between the solid and the liquid. Sorry, I should have said that earlier. And then here in the flat part, when you're at the boiling point, you're between liquid and gas. And then up here, it's just a gas. So we're going to purify a mole of aluminum at 298. The melting point is 933. And then it says the molar heat capacity is 24. The heat of fusion is 10.7. So the tricky part, part of the tricky part on this is typically when they give you the specific heat or the specific heat capacity is it's joules over grams Kelvin or grams degrees Celsius. In this case, though, they give you the molar heat capacity and they give it to you in moles. So when you're doing Q equals mc delta T, the one thing they're trying to do to mess with you here is instead of giving you, again, joules over grams Kelvin, they're giving you joules over moles Kelvin. which is fine, but just know that you can't use mass here then. You have to use moles. And hey, what do you know? They give you the amount of the aluminum in moles. So that's part of the tricky, part of our tricky part there. So basically what this equation becomes, anytime they give you moles in your specific heat, is this becomes basically N, which is what you would use like with the ideal gas equation, something like that. Okay, so the amount of heat it takes is Q equals N, so 1 mole, times the specific heat of aluminum, which is 24 joules over moles Kelvin. And just so you know that, again, the molar mass of aluminum is about 27. So that's less than 1 joules per gram Kelvin. It's still much, much lower than water is. Water, remember, has a specific heat of over 4. So this is still less than 1 in terms of grams. And then the temperature change is, again, we're originally at 298, so we're at room temperature, and we're going all the way up to 933. So the temperature change is going to be 933 minus 298. Okay, so I'm going to take 1 times 24 times 933 minus 298, and that equals 15,240. And again, that's joules. And that is now, because it is only 1 mole of aluminum, we can just say per mole. Normally, if they give you the grams there, you would have to convert the grams to moles and then divide, but since it's already in moles, we're good. Okay, so that is equal to 15.24 kilojoules per mole. And again, that is to get you from this part right here to this part right there. That's to get you to the melting point. Okay, and now for the melting process, they already give you, and again, that's where the delta H of fusion comes in, and they've already given that to us. The delta H of fusion is 10.7. So basically, we've got to take our first part here and then add it to that part there. So 15.24 plus our 10.7 kilojoules per mole is going to equal 25.9 kilojoules per mole. Okay, so that's one of the ways you can look at problems dealing with heating curves or cooling curves is the same thing. Here we can see this. Sometimes you will see where this will drop down a little bit lower and then come back up. So that part there won't be there. Okay, and when that happens, that's because it's called supercooling. Again, you're not going to see that on the AP test. So let's look at an example of this. A student investigates the physical properties of VbO2 and finds the following graph where thermal energy is added at a constant rate to a sample of VbO2, which is initially a solid at 0 degrees Celsius. The pressure is held constant throughout the heating process. Okay, so here we can see. So let's think first of all what's happening in this process. So here, remember again, solid to liquid, or no, sorry, 100% wrong. Here it's just a solid. Here it's solid to liquid. Here it's just a straight liquid. Here it's liquid to gas. And here it's just a straight gas. Okay, and then here on the bottom they've got time, and they're putting temperature over here on the side. So a student determines that the specific heat of VbO2 is 2 joules, and again, now we're back to grams. Determine the amount of thermal energy in joules that must be added to a 4.5 gram sample to raise the temperature from 40 to 55 degrees. Okay, so the amount of thermal energy in joules. So this is an enthalpy one. This is just a straight Q equals MC delta T. So, and again, the specific heat is given in joules per gram, so that makes it a little bit easier. So our mass is 4.5. Our specific heat is 2.0. And again, I'm leaving out the units just because I already know that they're all going to cancel anyway. And then 40 to 55 is a change of 15. So 4.5 times 2 is 9. 9 times 15. Q equals 135 joules is the correct response there. And then part B says, 2 intervals marked on the graph correspond to the time required for the temperature of the sample to increase by 15 degrees. Given that the sample is heated at a constant rate, explain why the time for 2 is greater than the time for 1. Okay, so notice that in time 1, you're in a straight liquid state the whole time, but in time 2, during a very large portion of that, those liquid particles are converting to a gas. And so again, that's the boiling point, the BP. And so that's when you're at the boiling point and you're heating it up, that temperature's not changing. Just like right here, when you're melting something, all of that energy that you're adding to it, all that temperature, that heat you're adding to it, is not being used to raise the temperature. It's used to either right here weaken the intermolecular forces, or here we're actually breaking the intermolecular forces. Okay? So why is that time so much longer on T2? Because so much of that energy that's being added is being used to break the intermolecular forces between the particles, where during T1, you're simply warming up that liquid to get to the boiling point. Okay? So during T2, this is the fancy way of saying it. During T2, the substance is going through a phase change, going from a liquid to a gas. The phase change absorbs energy in order to break the intermolecular forces between the particles, but the temperature doesn't change. So it takes longer to raise the temperature by 15 degrees during T2. Okay, part C says the student claims that the intermolecular attractions in liquid water, so the enthalpy of vaporization is 40, is stronger than those in liquid VBO2. The enthalpy of vaporization is 32. Do you agree or disagree with the student's claim? Justify your answer in terms of the relative values of delta H of vaporization. This is a good way, this is a good intermolecular forces type question. So they're saying that the intermolecular attractions in water is stronger than in VBO2, which means this is how much heat it takes to convert all of that liquid water into a gas. And this is how much energy it takes to convert all of the liquid VBO2 into a gas. And since water has a greater enthalpy of vaporization, that means it takes more energy, and so therefore the attractions between water are stronger. Okay, and that's what it says is stronger. Okay, so you're going to agree with that response because a larger or a greater value for delta H means it requires more energy to vaporize. And then therefore the attractions are stronger between the molecules. Okay, number 3, a student investigates physical properties of VrO2 and finds the following graph where the thermal energy is removed at a constant rate, which is initially at 165. So here we're at 165. Pressure's constant. Now here, notice again, we're going from gas to liquid, liquid to solid, and then we're just at a solid. Okay, now same thing here. Notice that time 1 is much larger than time 2. Okay, 2 time intervals are given. Given that the sample is cooled at a constant rate, so they're lowering the temperature, they're removing heat at a constant rate. Why is T1 basically longer? Why does it take more time than T2 does? Okay, remember that when it's a gas, those particles are completely independent of each other. Okay, when it's a liquid, they're already together. They just have to get into a position where they're not going to move anymore. Okay, so clearly this is showing that this is again, the enthalpy of vaporization in the reverse process, okay, is greater than, what we would call here the enthalpy of fusion, again, the opposite direction, okay? And therefore, the reason that has to happen, clearly you have to get rid of more energy in order for that to happen. Okay, and notice that your answer here, you don't even need to explain why. Okay, you really just have to say, well, if this one is bigger than this one, then that means that more energy has to be released for that process to occur. And that's all that they ask for you to say there. Okay, and then letter B, the student claims that the intermolecular attractions in liquid SO2 has a boiling point of -10 are weaker than those in liquid VRO2. Do you agree or disagree with the student's claim? So in liquid VRO2, let's see. So we're talking about, what are we talking about? The boiling point. So what's the boiling point of VRO2? Again, it's right here. It's that point right there. Here's the freezing point. So whatever that is, 70 or so. But then the boiling point would be 120. Okay? So if VRO2 has a boiling point of 120, SO2 has a boiling point of -10, what does that tell you about the attractions between them? Is certainly that the attractions in VRO2 are stronger. Okay? So the student claims that the attractions in SO2 are weaker, and that is absolutely true. So we are going to agree with that, and we would say a lower boiling point means the attractions between the molecules are weaker. Okay? And that's all you'd have to say there. Okay, and those are some good example questions there of some different problems involving heating and cooling curves. And even this one here, the one that with aluminum, even though you don't see the heating or cooling curve, that definitely is a problem where, okay, where are we starting? Right here. Where do we need to get? Right here. And let's combine those two together.